Hello and welcome. My name is Piers Ridyard, CEO of RDX Works, and here I have Dan, the founder of RDX Works and the creator of much of the research and technology that has gone into Radix protocol. Today we're going to be answering your questions from the community, and we have some great questions. So I'm going to start off immediately with the one at the top and go through in order because that's what it comes up for me on the piece of paper that I'm reading from. So, hey, Dan, there are some challenges presented in the shift to quantum computing. Is this something that's on the team's radar? And if so, what amount of work would be involved to update the Radix network to support these new cryptographic methods? I think this is like the project that had triggered this was a project called Cell, what it's trying to do is quantum proof or sort of like quantum resistant cryptography in their network to try and like shortcut the problem that's coming down the line. But yeah, it'd be great to get your thoughts on all of that.
Yeah, it's just like quantum resistance and stuff. It's a topic that comes up regularly, not just like for us, but just generally across the crypto space. But obviously, it's very relevant to just all of our digital lives, right? Like your banking app, emails, messages, everything that you do is secured by cryptography that is vulnerable to quantum computer stuff, right? And so this is something that I think all projects keep an eye on, kind of on the sidelines, see what current research is happening, where things are moving. But I think there's still a lot of research that needs to happen before you can really kind of tackle this problem with a vengeance, right? So like there are quantum resistant primitives already for cryptography where you can have, key signing pairs and things that are quantum resistant. But there's some complexity around how some of them work. So some of them are what's called stateful, right? So you need to remember, for example, okay, I used this public key in the past. I can't use it again, right? I can't use this key pair again. I got to remember what I've used. And other like little intricacies and complexities like that. There's a lot of research going on around stateless quantum resistant signature schemes and primitives and stuff. But it's not really there yet. Now, from the point of view of how would you incorporate these things, it's not actually that difficult to upgrade, as it were, your cryptography primitives, right? So you can from the kind of technology stack point of view, you can make that quite abstract, right? So you just have this thing that is sign this thing, verify this thing, and then that can utilize any primitives that have those functions. Well, your crypto primitives all have sign this thing, verify this thing, right? And so you can actually abstract away the actual legwork of whatever primitive you're using. So it might be, elliptic curve, it might be some kind of threshold signature scheme, BLS or whatever, ring signatures, et cetera, et cetera. You can kind of abstract that all away. So actually implementing a quantum resistant signature verification primitive isn't a lot of work. You just build a new module that plugs into this thing and you call it. Where the real problem is, I think, is that, well, what happens to all the stuff that was signed and verified prior, right? Or stuff that was encrypted? Like, what happens to all of that, right? Because you might not be able to go and re-sign those things with a quantum resistant key because maybe that key isn't used anymore. Maybe it was an ephemeral key or whatever. Or you might not be able to re-encrypt this thing because the user that encrypted it isn't around anymore. They've passed away or they're just not in the space anymore or whatever, right? So you have this this cryptology debt, if you like, right? Cryptography debt where it's always going to be accessible at the point of some kind of quantum breakthrough. So I think that's really the main challenge. It's not so much how do you upgrade your system to use these new crypto primitives. It's more about, okay, what about the stuff that happened? How does that get protected? And like that, it's just not there yet. I don't think there's a lot of complexity still in how you have to use these things, and they're not really mature either. A lot of this stuff is quite recent. So I don't think that it would be wise to deploy a public mainnet yet that had quantum resistant cryptography primitives as its main method of signing stuff, right? Because you need quite a bit of maturity time. And I don't think that we're going to have quantum computers around that can do this stuff, for at least another 5 or 6 years, at least not in the mainstream anyway.
Right. And I also, I had a real existential crisis about this, I don't know, 2 years ago. And I did a load of research about it. And I was like, and I wanted to understand more about why, what is the actual risk, and what are the problems that are presented by quantum. And so I found a few things that I thought were really interesting that helped me understand it a bit more, and also helped me feel a lot less worried about it. So the first thing I discovered was that there's a big difference between finding the private key and being able to pretend to sign something. So in quantum, what you are able to do with quantum is massively parallelize probabilistic operations. And so, when you have a hashing function, what a hashing function is doing is taking a very large piece of information and bringing it down to a very small piece of information and as a result, you lose a load of information in doing that. So you can actually create hashes that have the same output, what's called a hash collision. So I have two hashes that are the same, that are from a completely different data set.
I was just going to mention this, right? Because this comes up all the time about, what about hashes? So yeah, say you've got a 32 byte hash, right?
Right.
But you've got a document that's a megabyte, yeah?
Right.
Then there's going to be many collisions in of that document that produce a 32 byte hash that looks like the one you're after, right? But you're going to have a multiple of 1 megabyte outputs that, okay, well, which is the right one, right? Which is the one that corresponds to this hash? There could be millions of them, or trillions of them even, right? Like, which one of these actually corresponds to that hash?
So your quantum problem is that your output is actually huge. So that's one of the
massive
problems. So what quantum computing is really potentially risky for is what happens when you create a signature is you use a little piece of your private key and the transaction and do some maths and create something that means that you can prove that you had to have the private key to create this thing without revealing the private key. What that does, though, is it creates some extra information that it can be the input for quantum computing to do a probabilistic attack on.
And also with private public key pairs, you've got a one-to-one mapping, right? So usually, you've got a private key, which is the same length, depending on if you're using compressed curves or whatever, right? But it's the same length as your public key. So if you've got a public key, you can undo the one-way function to get the private key, because you will only end up with one private key output, right? But with hashes, it's not the same. It's not the same thing.
Right.
So which is why it's very dangerous for signatures and for encrypting things, right? Because you don't have a many-to-one relationship, right? It's not a one-way function. But for data, you definitely do. Like you imagine a 100 megabyte file, and you're trying to find which 100 megabyte file corresponds to this 32 byte hash. There's no way, right? You're going to be guessing your entire life which one's the right one.
Right. So the thing that quantum computing will attack first is this ability to, once you have a public key and you have signed using your private key, now that public key is vulnerable for a replay attack, for someone to be able to go, well, I can now guess what a signature to do a spend looks like. Not actually guess what the private key is, but guess what a signature to do the spend is. And so quantum computing, to be able to get to the point where you can replay. So when you have quantum dominance, the highest attack vector for a quantum dominance is that you can, when someone creates a signature on a transaction spend on their public key, and then someone has a quantum computer that is fast enough to be able to track that signature and then submit to the network before the first one is finalized, a competing spend that then spends to their address before it spends to your address. That's like quantum dominance. And that is like 30 years away at the most like optimistic for like Bitcoin, 10 minutes, right? 10 minutes confirmation time. And then like 70 years away for more regular. Now, this is one of the reasons that people often say you shouldn't use the same private key, public key repeatedly.
Because you're leaking information.
You should do a HDR, hierarchical deterministic, HDT, sorry, hierarchical deterministic tree. And so that every spends your current balance to a new place, and then that makes it harder for quantum to attack it.
Which is actually what a lot of the crypto-resistant primitives use. There's
anyway, right?
Like one-time pads and stuff like that, right?
Right, exactly. So you're
then
constantly...
That's where your statefulness comes in, because you need to remember, well, okay, which one-time key pair have I used?
Right.
But if I remember correctly, I think it's worse for symmetric keys, which is what most of the internet is built on.
Right.
Where you actually don't need a message, you just need the public key, and you can recover the private key. I think that's correct. Whereas elliptic curve, what Bitcoin uses, is asymmetric, so you've got data loss between them.
Right, and all of crypto is basically asymmetric.
Yeah, so it's basically it's symmetric. But if you're using your banking app, then that probably uses a symmetric RSA key, and so you're a bit more vulnerable there. But still, it's decades out, really.
Right, decades out from the point that in-flight transactions are at risk. And because a network is like Radix is finality, it has finality, it's got 5-second finality. The probability, the ability for a quantum computer to come in within 5 seconds and take something in the mempool and steal it is minuscule. We are talking like at least 100 years out for that kind of thing. For quantum computing, it's that far out.
I'm not sure I'd say 100 years. I think once you have, I think you will find that once you have a version of a quantum computer that can do this, sufficient qubit length, I think you'll actually find the improvements come really quick. So it's more about, it's like microchip, right? The first microchip took a long time to come after the transistor was invented. But then once that first microchip, just an explosion in terms of performance, right? I think you'll find the same.
I'll have to find the paper I read. The paper I read was assuming that. It was assuming that quantum would follow the same progression of...
The real question is, when do you have this first kind of general purpose, for want of a better term, quantum computer that can unravel these NP hard issues of,
So from my research, we're like 30 years off the replay attack of like spending a transaction in flight at least. And then from the point of view of like actually decrypting something, like that's a whole nother level again of complexity.
You need some serious qubit levels for that.
Right. So that's we don't need to worry about encrypted data yet. We like signatures are a subset that are a lot more vulnerable.
Yeah.
And so what these companies are doing is they're playing on this like sort of existential crisis that people have towards quantum computing. But what I sort of found was that we've got quite a while, and actually the research into quantum resistant cryptography is progressing well, but it's still early. Like we don't want to rely on cryptography that's just been created. You want it to be
you want it to be mature and tested and battle tested in non-critical systems, which is usually where it plays out first. Like they're critical from the point of view of some degree of the user. It's important, but they're not critical in terms of it's propping up an entire infrastructure.
Right. So in 10 years. Quantum is not going to yet be a risk to crypto of the type that Radix is, the Radix ledger. Yeah. We will have better quantum resistant algorithms, and we are actually making everything in Radix modular so that we can swap out our signature schemes and all that kind of stuff. So it's like for us, it's just yes, we understand there's a problem there, but it's a long way off. There's a lot more things that are more pressing and problematic for the crypto space today than quantum resistance is. And adding what these early, untested, not really battle hardened, and actually much larger and clunkier signature schemes to these ledgers is just going to make the ledgers slower and less user friendly for a problem that isn't actually present and real right now and isn't going to be for a long time. So that's sort of our approach, right?
Yeah. There's going to be smoke at some point, but the fire isn't there yet. So you'll be diverting attention to something that isn't as urgent as it's made to seem.
Right. And if we're wrong, that's fine. We built it modular so that we can and
you can guarantee as well is that as soon as there is some real threat that it's coming down the pipe in the next 2 years, there'll be a lot of attention on crypto secure primitives. Like, look how quickly the cryptography space is evolving, just because we've now got decentralized ledgers that hold a lot of value, right? And all these new different types of primitives that are coming along to facilitate the movement of that value. Like 10 years ago, nobody even knew what snark was, right? And or like elliptic curve signatures, 20 years ago, I think were not a thing.
Right. And now we've got like BLS, and we've got threshold, and we've got, like, as you say,
so much movement. So you can guarantee that, once there is a real on the doorstep quantum computer threat, then all the smart minds in this space will be like, we need to protect our bags. And it'll get solved real sharp quick.
Right.
So yeah, I'm not too worried. Just keep an eye on it, right? That's the thing. It's one of them smoldering things, and just keep an eye on it. It's really interesting as well, just as a stuff to get into as well. So it's a secondary reason for staying on top of it. It's interesting.
All right. Next question from Don Logan. Is Radix based on Chainspace? What percentage of Cerberus code, if any, is from Chainspace?
None. Bit of a strange question. I'm clearly missing some context here somewhere.
I think that when in one of the early AMAs or something like that, maybe with Matt or with Josh, maybe Josh speaking in one of the channels, people were talking about what's similar and what have we looked at, and Chainspace wrote a really interesting paper that had some very good thinking around how to do sharding, how to do
there was some overlapping ideas and philosophies, definitely.
And then Facebook,
but it's not the same thing. It's like saying is a jet fighter and a commercial aircraft the same because it's got a wing. It's like, well, no, not really. Like, same principle, some ideas are the same, but
also Chainspace's code was very early. Like it was if I remember correctly, and I may not, because as I say, we haven't really used any of Chainspace's stuff. It was just it was interesting to find another team that had some interesting thoughts in the crypto space.
Yeah, it was nice for validation. We're not crazy after all. Some other people in their own white room somewhere have come up with a few things that are similar to our thinking, but the solution to these problems isn't just one idea; it's many. And
but Facebook bought the team.
Yeah,
like
Facebook bought them. Yeah,
Chainspace, and then basically did nothing with it, then used like basically vanilla hot stuff for Libra, now DM,
which then never happened because Congress was it Congress or whoever it was.
Yeah, Congress got upset. They were like, U.S. sovereign money, it's our money. Stop playing around. No. Yeah. The existential crisis of the tech company, right?
Yeah. So no, there's no Chainspace code in there. Just a bunch of smart guys that had some similar ideas on some things to us.
Right. Next question from Chris is have smart contracts on a sharded Cerberus been demonstrated, or is it still purely theoretical?
No, it's been demonstrated. And most of you guys have probably played with them because the Twitter demonstration, the tweets, are essentially smart contracts. So if you think about when you reply to something on Twitter, right? You put your text in and you press send. But it doesn't just go and sit on a server somewhere. There's some tasks that have to happen, right? So if you're replying to someone's tweet, then it increments a counter on their reply. If you like it, it increments the like, et cetera, et cetera. And so those operations, they're like just your fundamental operations of a smart contract, right? Addition, subtraction, moving things around, updating the state on something. So the tweets are essentially smart contracts. And you've all played with that, and you've all seen that it's sharded in the Cassandra demonstrations. So, yeah, and it's just a basic one, but the fundamentals are the same, right? You take some state, you change it, you do something with it, you write it back.
Right, and this was a big part of your research as well around the state model stuff, right?
Yeah, state model, how you do it cross shard, how you do it without having to have long-lived state locks and stuff. And so once again, as I've said many times, the Twitter demonstration is a really good first kind of litmus test for all this stuff, because it's quite a basic demonstration, but it touches all the right parts, right? And gives a lot of information. Now, obviously, there comes a time when that particular demonstration outlives its usefulness, because then you want to start to try and do more complex things. And so then, you build the more complex demonstrations to get a bit deeper into some of these things. But yeah, technically, the smart contracts have been demonstrated.
Right. And this is all sort of like part of what Cassandra is for, as a sort of like research playground, that where you can do things in a sort of a more hacky way, but like take the shortest route between idea and implementation, that doesn't have to think about this being, sort of like high integrity, high reliability software.
No, it's just, does this idea even work?
Yeah.
And if it does work, what are the problems, regardless of my shitty code?
Right.
Because I've got there real fast with it.
And it's a good question, because like a lot of time there is a difference between theory and practice, and so taking the time to actually implement
sometimes you can have perfect theory that you just can't implement at all. And not just in computer science, but in any discipline, right? You have a theory of something and it looks good, all the mathematics checks out, all the common sense logic checks out, but you try and build it and it's like, I haven't got the right tools, I haven't got the right building blocks, and the building blocks themselves violate physics, so I can never build this thing. I'm not violating physics here, thankfully, so that's good.
All right, next question is from a guy called AS. The Quadrilemma has been solved. Statement of fact. Decentralized Twitter has been presented. What is left that takes so long for Xi'an or even Babylon to be released? I understand that Scrypto is one big point, but it will be released end of year. So what is the technical problem with releasing Xi'an in, let's say, the middle of next year? Or is it more strategic than technical?
Okay. So I think of the Wright brothers, right? And they demonstrated technically that they could fly. Yeah. Would you jump on that plane and fly across the Atlantic Ocean right now? No, you definitely wouldn't, right? You definitely want some maturity of that particular device. It flies off the ground. It does what it says it's going to do. It's a plane. It flies. But I don't want to do transatlantic flight on that thing the day after, because it's got no cabin. It's got no pressurized air. It's like, is it just going to fall out of the sky at some point? Like, how long can it fly for? How reliable is it? How good is it? Right. And so Cassandra is that plane, basically, right? It's been just what we're just talking about. It's been put together very quickly to get from theory to implementation and prove the technicalities of it very quickly. But I wouldn't want to suddenly go and throw $5 billion of value onto Cassandra right now, because there's still a lot of work to do. It's got no seats, right? It's got no luggage compartment. It's got no fail-safe systems. It's got no GPS. It just flies. That's all it does. It flies, and it shows that you can fly. In Cassandra's case, fly fucking fast, right? But right. you wouldn't want to do a transatlantic flight on it right now, and that's why Xi'an is long ways out, because even though the fundamental theories are proven, right? You can do this sharding, you can do it at scale, it scales linearly, you can do all these like cool smart contracty things, and state sharding and scales, and you can throw nodes at it and all that cool stuff. Great, that's great, right? That's really good. But there's still a lot to test, there's still a lot to harden, there's still a lot to build, right? You've got to build this thing probably from scratch, because you probably don't want to use my Cassandra code for the most part. So you've got to take my Cassandra code as a reference, right? Okay, it's got wings, it's got wheels, there's like a place for the pilot to sit, and he's got these sticks. But you probably want to take the implementation of that theory and redo it and build it on top of something that's already solid, and not just go lob it on.
Yeah, and just like sort of to sort of bring, like, reinforce that a bit as well. Like when you build public ledger systems, they aren't the same as normal software systems. They're much closer to hardware. I always say it feels like shipping hardware, because, if you're building a car and you ship it, it's really difficult to change something once it's out there, and it has to run
like a recall. A recall is a real headache.
A real recall is incredibly painful, incredibly damaging, has actually killed entire car companies if they're big enough. And but you still have to have something that can go out there and run for 100,000, 200,000, 300,000 miles and not break down. And so the engineering that goes into a one-off production of, like, someone can go into a garage and build a one-off car. That's not actually the hard thing. The hard thing is making that into a repeatable process that you can do at scale, that has like a parts per million failure rate that is acceptable at mass scale. Now, in public decentralized ledgers, you aren't building a system that is 99% reliable or 95% reliable. You have to build a system that is 100% reliable at all times. And yes, you can sometimes get, like, early systems will still have some niggles to go through, but the first thing you have to be is like, is this a safe place for people to keep tokens, to keep value? And guaranteeing that is like, you can build a model that works in most cases, but then you have to deal with all of the edge cases that a system can get into, all of the ways in which a network can like behave in weird ways when you get to scale, and all of the
the real problem there as well is, like, it's not like there's a list, right? So you don't have a list of, okay, this could go wrong, that could go wrong, that could go wrong. You've got to generalize that solution, right? Because there is always things that you don't consider, right? Even if you're manufacturing a car, there's things that happen out in the wild when someone's driving that car that you will not have thought of in the lab. And if it's a popular car, you've got that times a million, right? So you can't have a list of if this, then do that, because it'd just be endless, right? And you couldn't even think of all the things if you wanted to. So you've got to generalize the solution to this huge list of problems. And make sure that your generalization is broad enough and generic enough that it catches all possible edge cases. Now, obviously, there are some bounds, right? You can put bounds on that and you say, well, the 33% thing, that's a bound, right? That's an accepted bound. You can't get better than that. Well, you can, but you need like latency and stuff, right? But generally, your bounds are set by use case and computer science. So your solutions to all these possible edge cases and things that you don't know about and things that you couldn't have foreseen, that's hard. It's hard to generalize against a set of problems that you don't know.
Right. And I think that people, it's actually really difficult to properly to communicate how much engineering has to go into making something into a production system. And then if you add on top of that a production system that has to run outside of your control for the rest of foreseeable future, like, that is a really, really difficult engineering task, and it takes a very long time. So, Xi'an still has some a bunch of unanswered questions. Like, what Cassandra is doing is showing some good potential research solutions to that, but we still have to go through and sort of do the validation of it. And some of this is actually in test code, like the test suites of Twitter, and then some of it is just academic validation and like sitting down and doing the maths proofs and working through all these sort of like the actual bounds and the proofs around the bounds. And then there's the rest of it of going, well, we already have a system in flight, right? We already have value in flight. We already have people staking. We're going to already have smart contracts on it. We're going to have DeFi living on it. By Xi'an, Babylon will already have happened, and there will be hopefully billions and billions and billions of dollars in flight, in situ happening. That's not a trivial thing to build out. You're talking about as Dan likes to say, swapping out an engine whilst you're driving down the motorway. Ethereum is in the process of doing it, and you can see the complexity of that. Now, we built Cerberus to be we knew what our end state was going to be, so we're going to have an easier job of it than Ethereum has or any other ledger has, because our roadmap was set. We knew what our end state was. We were designing how we were building all of that, but that doesn't change the fact that there's a huge amount of value riding on getting all of this right. And so all of the ways you have to build these systems is an incredibly defensive model, which is why Cassandra is so good, is because it doesn't have to have any value on it. It doesn't have any value on it. So you can be
doesn't have
much
to be
more
defensive either. It can just say, okay, I need to answer some questions. These are the broad questions I need to answer. Open file, click new, no limitations, right? Just follow all the breadcrumbs. Now, sure, there are going to be lots of smaller questions that are very relevant to the product, right? Like, the Babylon out there and the integration points with Babylon and all this kind of stuff. But the smaller questions aren't the purpose of Cassandra. Cassandra is what are the train stopper questions and how do you solve them? And any questions after those train stopper ones are easier to solve. They're just more engineering problems than theoretical problems.
And just going back to the thing that we always say is like, scale doesn't matter if you don't have adoption, right? So like what we're focusing on is how do you make the best possible system for building decentralized finance, and how do you make the fastest time to talent for new DeFi developers and entrepreneurs coming in and being able to build great things. And like what we already have is something that is 3.5 times more scalable than Ethereum. And it took Ethereum 3-4 years from their inception to actually get to the point where they were pushing really against the scalability barrier frequently. So like, even if we do fantastically and smash all of our expectation, like Xi'an is well within the timeline that we like, even in the best, most optimistic possible scenarios, that we need more scalability than we already have on our roadmap. And, concentrating on the right things first, of like the people that want to use these applications, the applications having a fantastic basis for being able to build, the next wave of DeFi. Like those are the things that matter first. And then scalability matters. Yes, it's an existential crisis right now in Ethereum and other ledgers, but like what we've already got is a really good engineering solution for what is necessary to get to first, second, even third and fourth stages of this ecosystem. And then Xi'an comes in and just means that once you can just add fuel to that fire and just absolutely scale massively beyond that. But like, if we're pushing the limits of the network before Xi'an, great problem to have, but I would genuinely be astounded.
And there are solutions for that as well. There are solutions for that too. That aren't too invasive either. I thought about that a little bit as well. So yeah, if there's demand for 100 or 150 TPS before Xi'an, then we can work that.
Actually, that brings me on to one of my last things about that I think few people realize, but I think is so exciting about the Radix engine and Scrypto, is that a lot of people don't even realize that the execution speed that is necessary to do like a DeFi application on, like the amount of gas that you need to do a DeFi application on Ethereum versus on Radix using the Radix engine in Scrypto. It's more, I think it's like 50-1 or something like that, or something around that. Matt's probably going to kill me if I'm putting out actual numbers here. So let's just say it's a lot more efficient. But from the point of view of, we're not talking about transactions here. We're actually talking about DeFi operations, and 100 DeFi operations per second on Radix, on the Radix ledger, versus the same quantity on Ethereum. Radix can already do a huge amount more. So it's not 3.5 times more scalable in terms of just pure TPS. Yes, it is. But actually in terms of execution of decentralized finance, it's actually sizably more scalable than Ethereum is. Like Ethereum does 15.
And most of the stuff that's in the top 10 as well, right?
Yes. And it's, Solana's weird implementation of the EVM plus their weird implementation of Rust in like Avalanche's implementation of the EVM in their subnets, like all of these things, like the EVM is IOPS bound on all networks and is actually a big it slows down these networks.
This is what you see with like Avalanche and and Hashgraph and stuff, right? And all these other guys are like, yeah, we can do X amount of thousands of TPS. But that's just a simple state flip transaction. What about smart contracts? 20.
Right. 30. I think that's exactly what happened with,
and it's because the EVM's so heavy, right? So heavy because it's Oh yeah, it's an EVM, right? There's it's built for everything, and it doesn't need to be, because like you would never build Pac-Man in
Right.
Solidity, would you? I
I
mean,
mean,
you've got no monitor to show the sprites on to start with, but it's too big a hammer for the job that it needs to do.
right. So I think that I'd say that we are very, very far from pushing the limits of what we're going to be able to do with what we already have as throughput. Xi'an is not a engineering priority, because it things like Scrypto and Babylon and the DeFi ecosystem come before, and honestly, what we already have there is going to be plenty sufficient for a decent amount of time, even in the most optimistic scenarios. All right, next question from Blindsight. Good to hear from Blindsight. On demand scaling economics, node incentives are decoupled as far as I can see from network traffic, since transaction fees are not used to reward node runners. How will the network incentivize additional nodes?
I mean, yeah, that's a ways out, right? Because at the moment we've got Olympia, Babylon, that are your stakers, your set of validators. But then once we move forward into Xi'an and beyond, then the economics model for node incentives and stuff will have to be different. But it's not on the to do right now. That's one of the more minor things, if you like, right? So don't need to answer that question right now for the stuff that I'm doing, for example, in Cassandra, because it's a lesser priority question, an issue, in my opinion.
It's a good question, right? Like, I understand, but we are going from a very simple fee model in Olympia to a much more sophisticated one in Babylon, and then a much more sophisticated one again in Xi'an. Like, all of that sort of incentivization structure schema will be part of the design thinking that comes in once we have like more specificity around how the execution model looks for example, for Scrypto on Babylon, and then how the state sharding model is actually going to look on Xi'an, and the execution model combined.
Plus, as well, there's your fee model,
right?
Especially for some of this stuff, is very much associated with benchmark performance, right? So you need to look at what your baseline performance is given some baseline specification of machine when you're running this kind of stuff, and you can't get that until you're into your implementation stage. So for some of these things, can't even answer all of the question until you have an implementation that's functioning, so you can baseline it all and say, okay, you know what, we overestimated what this would be, but it's okay, implementation baseline says this, so we can adjust that. So
the economic model is always is for it to actually work is always going to have to be cost plus. Like, it's going to have to be like, it will have to reflect the economic cost of adding computing to the network, plus some like extra that incentivizes people to want to do it. Like, the crypto economics of incentivizing people to provide hardware and computing and resource to a network is kind of well understood at this point. But you have to start with going, well, what is the economic cost, and how do we create a way in which that like automatically finds a balance in the network without you needing a central party to sort of just like turn the lever manually. We've seen bidding as like a solution, which is what you have in Ethereum and a few others. Like, Vitalik has talked a lot about how bidding, like the top price bidding isn't the best model for it, and there's more like sophisticated ones coming down the line. So we'll certainly be pulling from other networks and how they're thinking at the same time as we're building our own thinking out on this. But yeah, like get it, making sure the execution model works, making sure the state model works, all that kind of stuff comes first, and then later we can come in and go, well, how do we make sure that the network constantly has the right amount of resources, is right sizing itself for the throughput that's necessary, for the execution that's necessary, for the storage that's necessary. Okay, so next question is regarding finality. It's from Charlie. And regarding finality, are there any ways that it can be reduced to 1 second levels? And he goes on, for financial applications, I think 10 seconds is fine, but on the morning commute, I just don't know if it is fast enough. Waiting 10 seconds for a payment for coffee is a decently long time. Same for buying a packet of crisps. For tapping into public transport, it's completely inadequate. Though for public transport, dedicated cards can be used, but being forced to use them feels like a step backwards. Musing on the topics. I know consensus is deterministic, but is there any probabilistic portion within a transaction, e.g. within 2 seconds, a transaction is almost certainly going to go through. Layer 2s have crossed my mind, as I think that the transaction you want for very fast finality, you generally don't care about AC. I'm not sure what AC is. So yeah, like talk about finality and sufficientness of finality.
So when you're going after really fast finality, right? Like sub 5 seconds, definitely sub 3 seconds. You get to the point where you have to start trading off decentralization. You have to. So if you've got a large set of validators, then even if all of those validators weren't, say, voting on something, right? Mm-hmm. So they're not doing any kind of voting stuff. They're just receiving information, yeah? Such as like with proof of work, right? Then the more validators you've got, then the longer it takes for that information to bounce along the validators, right? So if you've got tens of thousands of them, then for that information to propagate from a single source, because you've got a miner, you've got one miner that's produced that block, and that 1 megabyte block, whatever size it is got to propagate out to 10,000 other validators, right? Or miners in this case, yeah, full nodes and stuff. And the reason you need that, of course, is because me as a miner, I don't want to be mining on an old block, right? I want to be mining on the very latest one, yeah, all the time. Otherwise, I'm just wasting hash power, and that hash power could be used for me to.
So you're talking about Bitcoin here?
Yeah, just Bitcoin, for instance, right? Just starting off with, yeah. But so you want the latency between a new block being mined and me hearing about it as short as possible. Mm-hmm. The problem with that is there is a speed limit to that. One, you've got the speed of light, and then two, you've got how quick does the relaying node. So I'm another miner. I've received this block. Yeah, it's taken some time, speed of light from whoever sent it to me. I check it. Oh yeah, it's all good. Then I send it on to the next people, right? There's some latency there as well. Now that latency can reduce over time, Moore's law, et cetera, et cetera. Yeah, but the speed of light, that's fixed, right? It's as quick as you're going to get. So there is a lower bound to how quick you can propagate information across a network. Yeah? And there's some fancy maths that you can do that tells you what this is, given a group size of n and some information you want to send, and what is the average distance between relay nodes, right? Now, in a big network, especially if you're using determinism, let's say, right, where nodes are actually voting, you need at least 67% of all of the network to have seen this particular thing before it can vote on it, right? So then that is your ultimate lower bound. So if you want to go faster than that lower bound, you need to decrease the number of parties that need to see this thing in order to act upon it, right? Whether to vote on it or to do something with it or whatever, yeah? Now, to get below 1 second, then there's 2 ways you do it. Everybody who's having to talk to each other and vote on this thing, you reduce the average distance between them, right? So you stick them all in the UK, stick them in Scotland somewhere, right? Or in Iceland, you can use geothermal cooling for all those tens of thousands of machines you've got. So you reduce the distance between them, so the transit time of the messages is less, yeah, because you're still getting at the speed of light or close to. Or you reduce the number of people who have to talk to each other. And that's what most scalable networks choose to do, right? They reduce the number of parties that have to talk to each other, or they partition them some way, or have sortition groups or whatever, right? Networks that aren't chasing after a finality time, then they have larger groups because, well, the communication latency isn't too much of a problem. We can retain decentralization. And that doesn't mean that you can't have throughput scale, right? Even with long latency, you can have stupidly high throughput. It just means that your time to finality is longer. So I might be able to to process millions of transactions a second, but each one has a finality of, say, a minute, right? So that's why in like I usually quote that probably the useful lower bound for a large scale network that we can probably achieve is maybe 5 seconds, between 5 and 10, because below that you need to start doing lots of tricks. You need to start to reduce your validator count, etc., which we obviously don't want to do. So, even if you went down, say, a probabilistic route with that as well, right? It'd still be very difficult to get it below a second and keep your scale, your decentralization, because you've still got to communicate whatever it is that alters the probability of that thing being final, right? Everybody's still got to see it. So they go, okay, cool. So now the probability has dropped from 50% to 25%. So you still hit the same bounds.
Right. And there's nothing stopping people using payment channels for things like this as well. Like, I think that if you really, really want to get that low latency, payment channels are still quite likely to be what ends up getting used. You have two portions of this. One is like two parties that want to interact at speed, and Bitcoin's Lightning network's a really interesting use case for small payments. What is happening in ZK rollups is really interesting for small payments or fast payments. The thing that we sort of focus on a lot is this idea of being able to compose together lots of applications, but there you don't care about finality time as much as just making sure that everything is final or nothing is final. So it's like, if I'm composing together something in Uniswap across to from Aave to Uniswap to SushiSwap and back to Aave, I don't care so much that it's taken 5 seconds or 10 seconds to be final. I care that either the trade succeeded between all of them or failed between all of them, and that's far more important for the finance side of things, and like sort of ensuring liquidity and ensuring sort of like price stays at the right level. If you start going down towards like quant trading and you start going towards sort of payment rails where you have sub-second finality for sort of like user tap in tap out, like it's quite likely that infrastructure is going to have some sort of like channel-based payment systems that like use the main Radix ledger as settlement, but for the aggregation of very large numbers of small transactions, like it makes sense to start using things like ZK rollups.
Yeah, I mean, you can build layers on top of these things, right? Like, and it also depends a lot on what your topology, your state topology looks like, right? Mm-hmm. So if you aren't a sharded network, then there's a lot of things you can do to cut down that finality time, right? Like if you're say using hot stuff, this isn't anything that we're going to do. I'm just brainstorming out, right? If you're using hot stuff or say PBFT or some deterministic consensus that's got a leader, then if I really wanted fast finality, I could just send my transaction to the leader. The leader could do some pre-verification of it and give me this is probably good, right? This probably failed. This will probably be good. So you can get a kind of pre-confirmation if you just do micro payments. Then is it a massive deal if your $2 coffee has a problem? Probably not. So if you really wanted that kind of fast finality stuff, you could do it that way. Mm-hmm. The real issue is when you're trying to scale up, right? When you're trying to scale up your throughput and you're trying to keep your decentralization and maintain your security. Because what you're going to end up then is, well, the way that most people do it is they shard the state set, right? Whether it's our method of sharding or somebody else's, like Zilliqa or anybody else who's doing sharding. The problem then you've got to communicate across different validator groups, right? And that is always going to add latency. So you've got the latency of your internal group communicating about what's going on, voting or seeing things or relaying stuff on, speed of light. Then you've got communication with another group somewhere. It's another set of speed of light communications. And then what if they aren't ready, right? So there's some transaction. Okay, we're here, we're ready. Send it to them. They aren't ready. You got to wait for them to be ready, right? You can't do it without them because then you won't get an agreement. So you got to wait for them, right? And the more groups that this transaction touches, then the more possibility is that you're going to have to wait for all of the groups to be ready to say, okay, yeah, I'm ready to vote on this now because something else I was doing conflicted with this if I'd have processed it right away. So I had to wait, finish that, and now I'm coming to do this.
I just realized
like,
that.
huh?
Sorry, go on. Okay, so go on. Sorry.
So like in sharded networks, then the likelihood of, well, I'm actually going to say like sub 1 second finality in sharded networks is never going to happen. Unless they're all packed in someone's bedroom, right? And I would definitely say that your best lowest potential is maybe 5 to 10 seconds on simple stuff.
I've actually just realized I actually need to talk to verify this with Matt, but I think that our transaction model may let you do something that circumvents all of this. So if I'm a coffee shop or a transport network, with the Radix transaction model, you can build the transaction and sign it and then hand it over to something else that can then submit it to the network. So you could almost see these transactions as like little checks, right? And what you do is you go, right, at the point of like tapping in on a bus, right? Actually, what's happening is you've just built the transaction, you've handed them over the transaction. You're like, here you go, here's the transaction. What that can do within sub-second finality is check to make sure that hasn't already been submitted to the network. Like that is valid for submission, right?
Yeah, which is basically what I've just been saying about giving it to the leader. Same principle.
No, but but in this case, it's just giving it to the company. Now the company is taking a choice to be like, I am happy to take the small credit risk of this failing.
Well, yeah, your company there could be the leader in my example, right? Here's
right,
the thing.
Exactly.
Do a quick check of it. Yeah, it looks good. It hasn't been spent already. Okay, right. I'll take this, right?
But basically taking that burden off the network and just going, me as a coffee shop, for me to get sub-second like customer payments, I'm happy to just take these checks, which are basically pre-submitted but valid transactions, and then I will just go, yep, transaction's good. They get their coffee. I'll be submitting them all in the background. And then the finality comes like 5 seconds later, 10 seconds later. But then the company is taking that small risk on someone doing a double spend on a $2 transaction. Like, what? Who's going to do that?
Somebody whose $2 is buys them food for a week.
Right. But if they have the sophistication to be able to double spend a $2 transaction,
I mean, yeah, like you do have a double spend window there, and it will happen. It will happen, right?
Right.
People will do it.
Right. But this is how you would also do payments on aeroplanes, for example, which don't have internet connection. It's like,
well, the good thing with payment on an airplane is that you got no internet either, right?
Right.
So you pay them on their terminal, and then as soon as the plane lands, they all get sent to the back end. Right. In the meantime, you're waiting for your roaming to kick in, and they've already settled by the time you go, okay, double spend that.
So I think with the payment, with the transaction model, you could absolutely build it in such a way that you could build a payment system that has sub-second confirmation time for the user, and then the company takes a small credit risk on the 10 seconds it takes to actually transmit that to the network and get finality. Yeah. I think that would be more than acceptable by most companies, considering actually the amount of credit risk you take in just taking card payments.
Yeah.
Chargebacks on coffee. Oh, I didn't get the coffee.
Right, exactly. But yeah, I think yeah, like from the question, like any high scale, like Ethereum, anybody who's building these things to scale up to X amount of hundreds of thousands of transactions, you're going to have latency that's lower bounded. I would say, yeah, definitely best 5-10 seconds. Are the tricks you can do to get around that? Yeah, sure. Right. I mentioned one, Piers mentioned one. It's really just about moving the risk, really. Right. So, like in my example, I'm moving the risk because I'm trusting the leader of, say, PPFT, the current leader, and in Piers' example, the coffee shop is taking the risk because they're trusting you.
Yeah. Next question. This is from Mr. M. Can royalties be adjusted along the way to adapt to demand? And if so, it would be quite annoying if royalties can be adjusted upwards, since there are probably high switching costs, big lock-in effects. How will this work? You want me to take that one?
Yeah, I mean, I'm not too deep into all the royalties stuff, so I don't know if I can answer this with any
Yeah, so
surety.
these are things that are still, we have. If you read our DeFi white paper, we're actually going to be publishing an update to that, which has got sort of some more mature thinking on things like this. You'll see that the royalty, the way the principles of the royalty system is quite flexible. There are like several different ways in which royalties can potentially be charged. The Some of the principles are like, once you've set a royalty, you can't adjust it upwards. I think that would be pretty like problematic for decentralized networks, as you say, with lock-in. So that's currently you can't adjust it upwards. I think there are a lot of thinking about how you can do things like volume discounts and stuff like that, which is obviously going to encourage people who are doing large volume not just to copy a component to remove that and just find a way that they have a happy equilibrium with the providers. But yeah, more details will be coming out about this soon. But certainly, it's an interesting area of research that we're looking at.
Yep.
And then last question. Last question is from Alan Simon, or Simon. Could you explain the execution model for Xi'an? Suppose there is a DEX on Xi'an and 100 different users simultaneously invoke the DEX to perform a Scrypto transaction that has the intent to swap 10 of my XRD for some USDC. It is my understanding that just before execution by Cerberus, a specific 10 XRD will be assigned for each of the 100 user requests. For maximum, no, that's not correct. For maximum execution parallelism, I expect that a single shard will perform the transaction execution for each user, and that each shard will be pseudo randomly chosen from the 2 to 256 shards, so that the execution of each user request occurs on a different shard. Is this correct? And if not, why? I mean, we covered this in the previous AMA.
Kind of,
in some depth.
but this is a little bit different. But it's okay, because this is something I want to talk about.
Okay.
Anyway, so I can't do this from the point of view of Xi'an, because we still don't have the seats and the nice air conditioning in the Xi'an plane yet. So I'm going to talk about my Wright brothers way of doing it, which may end up looking pretty similar, to be honest, right? So this touches on something that I saw on Twitter the other day called an earnings problem thing, right? Which was kind of interesting, because it definitely does highlight issues in the way that a lot of thinking with like the sharding models and state yanking models and stuff like that. And that problem is kind of akin to this a little bit, right? So the earnings report problem is, say you've got Apple, and on earnings report day, the earnings report is, it's great sentiment or whatever, so everyone rushes to buy Apple shares, right? And Apple, that stock lives on shard 1, let's say, right? So everyone just runs to shard 1. Then you've got Microsoft that are on, say, shard 2, and Google that are on shard 3, and those shards are just basically sitting idle because it's not earnings report day for them, so they're nicely ticking along, right? But then you get a bottleneck on the Apple shard because everyone wants Apple stock right now. Yeah. And then you've got an exchange or a DEX or something application running there that's doing all the trade matching, right? But the problem with that is you get a CryptoKitty situation where anything that's trying to go through shard 1 can't get through because you've got all the Apple trades going through there, right? So from the point of view of that earnings report problem here, I got thinking about it a little bit. And one of the nice things about our sharding model, where you have this 2256 shard space and you've got all these kind of substates just scattered around everywhere, you have a really nice uniform distribution of stuff, right? So if I had a high balance and I had lots of substates in my balance, then they'd be nicely distributed across this entire shard space. And so would peers and anything else out that I've got, my NFTs, my DeFi tokens, whatever they might be, right? It's not all in one place. And so that means that all of my substate that makes up my portfolio is also distributed nice and evenly across the validator groups as well, right? So it isn't all just concentrated in one particular group. It's, again, evenly-ish distributed by uniform distribution, some randomness in there, right? You get a few little peaks and troughs, but nothing crazy, across all the validator groups as well. So then if I was Apple, then all my Apple stock, or what could represent stock, things to buy, right, buy sell orders on a DEX, would also be distributed nicely across this entire shard space, right? So there's the sell side and the buy side, right? And that's all nicely distributed across all of this shard space, and therefore nicely distributed across all of these validator groups that are responsible for processing the transactions for those trades. So then on Apple earnings day, when everybody piles in to buy Apple stock, all of those additional trades are also nicely distributed across the shard space, right? Because you've got value coming from that shard over there to buy some stock over here, and so on and so forth, right? Because you get these emergent shards, as it were, in Cerberus, where these parties are interacting, these substates are interacting, so there's an emergent shard for them that gets processed by this group of validators that are responsible for that shard state. So you get a nice even load balancing, right? Except in the fact where you have some global state, right? So if you've got global state, then that can sometimes cause an issue, because especially if it's got a lot of contention upon it, right? Like if you've got millions of things that are trying to increment a single counter, then you've got to have some kind of scheduling, right? One of the solutions around that is you can do roll-up selection of transactions. I'm not talking about ZK roll-ups here. I'm talking about kind of a more mechanical, if you like, a lot simpler roll-up. Yeah. So if I'm a validator and I can see, of all of my mempool of transactions that I'm trying to process, 50% of them are trying to increment this counter. So I can just bundle all them together, and then I don't have to lock the counter once. I can process all those increments, and then I can unlock it, and the counter's in step 50 times, right? So you can reduce your contention. But there's some cases where, even though you have a global element, such as a price, right, there are certain circumstances where, even though it's global, you don't need to actually track it, right? So in a really thick market where you've got a thick distribution of buy and sell across an entire spectrum of shards, then you don't need to track a price, because you will essentially get a normalization of price across all of those shards. So what would happen here is you've just got this set of validators on this shard space have got a thick buy and sell book, and over here you've got a different thick buy and sell book. But because the market is all knowing, then you will have all of your spreads and depths will be similar across all of the trades and all the buy and sells across all of the shard space. You don't actually need to track a price. So in Amazon's case, in Apple's case either, with the specific earnings report problem that was mentioned on Twitter, then we wouldn't have the problem that is mentioned in there, because it's not bottlenecked in a single place. And even the global element, the price, isn't important here, because essentially what's happening, you're getting all these micro buy and sell border books, because the market for Apple would be so thick that you wouldn't actually need to track the price as well. So taking back to the actual question, so what would happen in the case of a trade, right? Well, in the case of a trade, you would have some buy over here that somebody's sent to the buy book, right? I've got a limit order or whatever, and I want to buy at something. So that sits over here. And then you've got somebody on the other side that's saying, well, I want to sell at this price, right? And that sits in a shard over there. Now, from the point of view of those users, the custody of the tokens that they're buying and selling, let's say it's Apple stock here, right? So it's Apple stock here, and let's say they're buying with XRD. The custody of those tokens will be now the DEX will be the custodian of those tokens, right? So I've sent some tokens in, and the DEX is responsible for the custody of those tokens to do the order matching, because the DEX doesn't want to do any order matching until it's got custody of, where's my liquidity on both sides that I'm matching. Same thing for an automated market maker as well, right? You've got to hand over custody of the tokens. Then, of course, it's all the not your keys, not your coins kind of thing goes on, but that's the same everywhere anyway, even the DEX. So you've got these two in the order book, and there's loads of buy and sells in the order book anyway, and each of the validators would have a smart contract process running every time, and you buy or sell custodian event came in. They would look at they would trigger that smart contract. They would look at, can I match anything here? Does that cause a buy and sell match in the market with anything that's on the buy side or anything on the sell side, depending on what the order is that the user is doing. And if it does, it gets matched. And if it doesn't, then it just goes and sits in the order book until another buy or sell event comes in that alters what the two sides of the order book look like. And then that matching engine again looks, okay, so does this match anything? Does this particular trade, this buy or sell that's coming, match anything on the buy or sell side? And from the point of view of the contract, then it can either have two things. It can either just have a balance of tokens that it has. So they've gone from being kind of substates to just a number balance that you can then convert a portion of that balance back into substate again and send it out to the user, and it lives in some shard somewhere. Or you could actually just hold all the UTXOs that represent those substates if you wanted to. But the point is that individual things come in to a custody, to the custody of the DEX. There's a matching engine that runs every time that event is a buy or sell event happens, a trade, limit, whatever. Matching engine runs. If it matches something, it then swaps the relevant amount of tokens, creates the substates, and sends them out to the user's wallets or whatever they are. It's not kind of pre-allocating XRD or anything. It's doing it on as it matches basis, right? Which as you would also have with like an AMM. You wouldn't say, okay, I'm going to pre-allocate all these 100 simultaneous users, because you don't know you're going to have 100 simultaneous users anyway, right? You can only see what's now, not what's coming. And those users would have some kind of order in the order book, so they might all hit simultaneously, but then consensus figures out, okay, well, what order are these in the order book? And then you can also do the roll-up thing, right? Like these 100 transactions have come in very quickly. They're all touching this particular function, which is doing a DEX swap or an AMM swap or whatever. Well, let's just pile all them into a single consensus event so that we don't have to keep unlocking things. So I think that basically covers the question, right?
Yeah, I think that some of the confusion here is like sort of what does the application have to care about, and what happens underneath the hood, which goes back to sort of what we're talking about in terms of the how the UTXO state model translates into application logic, and it's like you don't have to worry about that at the application layer.
Yeah.
The other thing I'd say is this question is one of those questions where it's really trying to engineer a situation that I just don't think is going to exist anyway. Like it's pre-assuming that there's only one venue for exchange. One of the incredible things that public ledgers do is they separate the concept of the asset for the venue for exchange. And so like on Ethereum, there is Uniswap and SushiSwap and DeFi Plaza and all of these other places that all trade the same assets. And so the idea that there's only one location to go on the ledger, even from the point of view of a DEX, to be able to trade something doesn't work. It doesn't actually match up to the reality of what's happening in DeFi. And then add on top of that, specialist routing programs like 1inch that will automatically route your trade to the right place given the liquidity and the pricing profile of what you want to do, and may spread them across multiple. Again, like the DeFi way of building things is way more complex and way more I'm multifaceted in terms of where the venues for exchanges and where you can move assets. And what we've done with how you represent assets means that the representation of assets is sharded. So like there isn't the Apple shard where all Apple shares exist. Yeah. There's the Apple state that is represented across all shards that it's been spent to. And then you'll have multiple dexes where you'll be able to trade these assets, like sort of these concepts of like, ideas in which you can
basically pigeonholing things, right? That's the concept. You're pigeonholing, and eventually you run out of holes, or your pigeons are too big to fit in the holes, right? Well, it's like, well, just have a lot of pigeonholes and small pigeons,
right?
Well, and in fact, don't even have pigeons, right? A wing lives over there. There's a leg in that hole. There's a head in that one. You got sub pigeons that live in all of these many unlimited holes, and then when you need to build a pigeon, you just grab bits of pigeons from all of these holes and put it together, and you do your thing.
I think we've gone to that weird place when we've been talking for too long.
Pigeons for the win. It's always pigeon.
It's
I think you're right as well, right? Like there will be multiple arenas where you're doing swaps. And the beautiful thing with it as well is, of course, you can just do one-to-one swaps with kind of like over the counter, as it were, right? You can just say, well, I want to sell a bunch of this Apple state that I've got, and I want some XRD state that you've got, and we can see all of these different DEXs and AMMs that are in this system. We can use them as a spot oracle for our particular trade, and off we go. Right. Don't even need to touch a DEX or an AMM. But then, obviously, that doesn't mean that there won't be a popular DEX somewhere that maybe does have this at some point, right?
Yeah,
well, fine. And you can rest assured that it's not going to trip it up.
On a particular asset pair, on a particular DEX, bearing in mind that there is no constraint on the underlying asset and there is no constraint on there not being multiple venues, there still could be a very popular DEX with a very particular popular asset pair for a particular point. And like when you get there, then there are other optimizations that can be applied, but it's going to be a long time. Again, like this going back to this whole thing of like, I think that a lot of people don't realize actually how much throughput even 100 transactions per second is, and like when you get to Xi'an, how much throughput 1,000 or 10,000 or 100,000 actually is.
Actually,
mind-boggling.
I've got a perfect example for this, right? Again, going back to the good old Twitter thing, right? So think about a popular person on Twitter, right? Musk, let's say, right? Musk makes a tweet, and within seconds, there's like thousands of replies, thousands of retweets, thousands of likes, right? Now, when I'm importing on the Cassandra demo, I'm importing Musk and all these other popular people on Twitter, right? It's the same thing there, right? I actually logged in as Musk in the Cassandra Twitter, and I hope to God Musk has got his notifications very strictly managed. Otherwise, it would drive him insane. I just sitting and watching the notifications come in for him. It's like, oh my God, I don't want to be Musk anymore. It's too stressful. So the point I'm making is, like, you've got Musk. Yeah, there's a single account that's living in a particular place, right? A pigeonhole, yeah. And then you've got all of his tweets that he makes, right? Now, when he makes a tweet, you get a ton of replies, right? Coming from different places in the ledger to this single resource, yeah, which is a reply. But that doesn't bottleneck Cassandra in the way that you might expect, right? Because most of it is just a read, yeah. I'm just reading, and I can do tricks like, well, all of these things are referencing that one single thing there. So I can just process all these at the same time. Even though they've come from different places, right? I can just process them all in a single roll-up, and I'm all good. But from Musk, the point of view of Musk's account, that's also a single thing sitting in a particular pigeonhole, yeah? But then you've got all these likes and retweets and replies and messages coming in from everywhere. But because Elon Musk's account is distributed across the entire shard space, you still don't get any bottleneck because the input is distributed and the output is also distributed. Musk's little thing, his profile in the middle, doesn't make any difference, right? All that's happening there is that, does this thing exist? It's just a read from somewhere. It's a non-locked read as well. I don't even need to lock it or do anything with it. It's just, does Elon Musk exist? Yes, he does. There's the proof. Cool. We can carry on. Don't need to talk to you anymore. So you can massively parallelize that as well.
Cool. All right. Well, I think we'll leave it there. Dan, as always, absolute pleasure talking. Always learn something new. And thank you, everyone in the community, for your...
Did we actually get through all the questions?
We did. We got through all of the questions.
Wow, that's the
first. We spent half an hour longer than we normally spend. We normally spend 45 minutes. We spent an hour and 15 minutes.
Oh, yeah. Wow.
But
very good.
It's been great. Thank you very much to everyone in the community who asked a question, and keep them coming.
Indeed. See you soon, guys.